Hello and welcome to this lecture on quantum computing and quantum information. This is a continuation of our theme on discussing experiments in quantum computing. Let's look at what we have in store today. Last lecture we discussed the DiVincenzo criterion, which was the set of constraints that an experimental system must fulfill to be able to do quantum computing. We understood decoherence and we also discussed some models of decoherence. We actually considered NMR, nuclear magnetic resonance, as an example of such a system. Today, let's see why there are problems with the NMR qubit, why it's unsuitable for quantum computing, and let's then move on to an alternative, which is trapped ions. So let's see why NMR is a bad qubit. NMR is a bad qubit because the nuclear magnetic resonance qubit is in what is called a pseudo-pure state. It is at an inverse temperature beta, which is given by 1 over kT. So the initial state of an NMR qubit can be written approximately as 1 plus beta h bar omega naught Iz. Let me remind you that the Iz is just half sigma z. And this tells us what the problem is. The problem is that even though we have access to a single qubit in the form of the sigma z or the Iz part of the density matrix, almost all of the population is in this maximally mixed state, which is given by the identity matrix. So what this means is that this qubit actually exhibits really bad signal to noise ratios, and it is unsuitable for large scale quantum computing. It's unsuitable for the scaling relationship in quantum computing. So let's look at an alternative, and as an alternative, let's look at trapped ions. To consider trapped ions as qubits, one must first discuss how to trap ions. So let me mention that typical ions that are trapped are calcium, beryllium, magnesium. And for trapping, one would like to take the simplest approach possible. So the simplest approach is to see if an electrostatic potential is able to trap an ion. After all, it's a charged particle. This is in general not possible and is a consequence of a theorem in electrostatics called Earnshaw's theorem. Let's take a look at it now. Earnshaw's theorem is just a simple statement that a source-free potential must obey the Laplace's equation del square V equals 0. Now, if we expand the del square, we can write this for a two-dimensional potential as d square V over dx square plus d square V over dy square equals 0. And now we see what the problem is. The problem is that if the curvature of the potential along the x-axis is positive, let's say the first term here is positive, then the second term has to necessarily be negative for these two to add to 0. What this means in a picture is that if V was the potential that I wanted to consider, and if I imagine that instead of a charged particle I just have a marble, and that V is a gravitational potential, then if the marble were moved a little bit along this axis, it would roll back gently to this place, just like a marble would sitting in the bottom of a hill. But with respect to this direction, it's on top of a hill. And if I perturb the marble a little bit towards this direction or the opposite direction going down, it would just roll away. And so this requirement that del square V equals 0 basically translates to the fact that there are no stable trapping potentials electrostatics offers to us. So what is the solution around it? The solution actually is available even in this analogy that I pointed out. So let's stick with the analogy of a saddle and a marble in a saddle, and let's see what can be done. So now imagine that instead of a stationary saddle, we have a saddle that is spinning about one of the axes that is indicated here. So consider this saddle to be spinning with a frequency omega. If this marble stationed at the center of this potential is now displaced a little bit, if omega is slow enough, then the marble simply rolls away. The saddle is turning the entire time, but the marble's motion is much faster than the saddle. So the spinning of the saddle has no effect on the marble being in an unstable potential. This problem has not been resolved. Now imagine the opposite limit, where the frequency with which the saddle is spun is rather fast. If this frequency is fast in comparison to the typical dynamics of the marble, let's say the amount of time that the marble takes to go from here to a little bit far away from here. If this frequency is much faster than that typical dynamics, then what happens is that before the marble has a chance to get away too far, the saddle has spun to a place where this potential is in the place of this potential. So what this means is that while the marble was trying to roll away, the potential spun around so that now it offers resistance to the marble's motion by increasing this height, right? So if you do this spinning quickly enough, what happens is that the marble finds itself to be localized around the center. And this basically is the solution to the problem that we are facing. This spinning saddle, basically, the way it breaks Earnshaw's theorem, to use a colloquial word, is that it takes this potential v of x comma y and introduces a time component to it. The frequency implies that there is a time component to it. And this time is crucial in this entire picture, because what it does is it allows us this additional degree of freedom to control this spin. So let's see how to translate that to trapping ions. So the spinning saddle idea inspired what is now called the Paul trap. The Paul trap consists of 4 electrodes, which I've indicated in red and green here, and the ions are along the z-axis on the center. Now, I described the fact that one must change the potential in a time-dependent fashion, and if we look at what happens to these electrodes, we see that whilst at time t equals 0, along the diagonal, the 2 electrodes are positively charged, which is to say that the potential is plus v naught over 2 cos omega t. Along the anti-diagonal, the potential is negative, which is to say it's minus v naught over 2 cos omega t. In a short time, what happens is that the polarity flips, and along the diagonal, the potential is negative, and along the anti-diagonal, the potential is positive. This spinning saddle is now emulated by the Paul trap by simply transforming the time-dependent potential in this way. What happens is that this prescription traps the ions along the axial direction. Let me point out that the axial direction is along this z. To analyze this a little bit further, let's look at the equations of motion involved. Let's start with the simplest equation of motion, which is the z equation of motion. One can derive that the z equation of motion is that of a simple harmonic oscillator. M d square z by dt square is proportional to the minus of z. This proportionality constant, which is the frequency, has terms such as q, which is the charge of the ion, m, which is the mass of the ion, L, which is the distance between the end caps, and V cap, which is the cap potential. Here I'm referring to 2 end caps which are on both sides of this diagram, which are also charged by an amount V cap. So this equation, of course, means that the motion of the ions is that of a simple harmonic oscillator. A detailed analysis also shows that there are additional modes along the z-axis, like this breathing mode that I have depicted here. Let's now consider the motion along the other 2 axes, which is the x and the y-axis. One can again derive the equations of motion along the x and the y-axis, and these equations of motion are given by what are known as the Matthew equations. I'll describe these equations to you. The differential equations have the familiar form of d square x over dt square is proportional to x, and d square y over dt square is proportional to y. But there is an additional time-dependent term which is cosine of omega t that enters both equations. We know where this cosine of omega t comes from. It comes from the fact that plus or minus v naught cosine of omega t divided by 2 was the choice of the modulation that we have chosen. Again, various constants enter this equation. Let me point out this constant a, which is related to the distance between the ions in the center and one of these rods, which is in the corner, right? So this ion and this rod. So along this direction, which is in the xy plane, that's the distance a. Now, These equations can also be solved, but let me actually show you a picture of what is happening. To do that, let's actually draw the saddle in a color plot. So here what I'm showing you is a contour plot where red indicates a lower potential, which means that an ion placed here and then gently pushed would just run away in that direction. That's the arrows. And blue indicates a higher potential, which means an ion that is placed here and pushed would gently roll back into the center. As we spin this potential very, very quickly, the ion basically executes motion about the center. This motion looks like this. What I have done here is I've greatly exaggerated both axes, and I'm describing to you two kinds of motion. The first of these is what's called the center of mass motion, which is just the fact that this ion just rolls around the center. The second is an extremely rapid motion that I've depicted here, and this is called micromotion, and is a consequence of the fact that the potential is spinning rapidly underneath. Micromotion contributes to the heating of ions because it increases the number of phonons in the vibrational degrees of freedom. So what we have are trapped ions that are rather hot, and this is no good for quantum computing again. So what do we do about this? We have to cool these ions. So let me describe to you two mechanisms that one uses to cool ions. The first of these is what is known as Doppler cooling. If we want to cool ions down to around 15 phonons, we can appeal to something called Doppler cooling. Doppler cooling is based on the Doppler effect and is described by the cartoon that is given here. So imagine that an atom is moving in a particular direction, and if electromagnetic radiation is incident on this atom such that it has a lower frequency than the transition of the atom, then because the atom is moving towards the electromagnetic field, it can absorb a photon. When it absorbs a photon, because the photon is moving in the direction that is opposite to that of the ion loses momentum and hence cools down. By repeating this over and over again, one can cool these ions to around 15 phonons. 15 phonons, it turns out, is not good enough for quantum computing still. One must get these ions as cold as possible. And to do that, one has to do what is known as sideband cooling. So let me describe to you sideband cooling briefly now. Consider the following abstract problem. So imagine that you have an atom which has many energy levels and which has a particularly narrow energy gap. Furthermore, imagine that the damping rates of this atom are rather slow as well. Now consider the following scenario where the temperature sets a scale kBT, which is much larger than the atomic frequency gap. What this means is that the state of the atom is a thermal state given by e to the minus beta h divided by the partition function. Here h refers to just the bare Hamiltonian of the atom. Consequently, an energy level Ek somewhere in the middle is occupied with probability e to the minus beta Ek. This is the Boltzmann distribution factor. What this means is that this qubit is no longer in the ground state, and it breaks one of the assumptions that is made in the De Vincenzo criterion list. Remember that criterion 2 was that we must be able to initialize this quantum system in the ground state. And because of this thermal occupancy, this atom is no longer in the ground state. So we wish to cool this atom. What do we do? What we should do is, in fact, to bring another atom which has a much larger spacing and which is damped really, really fast by some rate kappa. Now, because this atom has an energy level spacing much larger than the temperature scale, and because it is damped really fast, it's almost always going to be in the ground state, which is to say that the density matrix of this atom is quite well approximated by the ground state. Now, what this means is that our target atom has a lot of entropy in it, whereas the auxiliary atom that we have just brought in has almost no entropy in it. Sideband cooling is a technique that allows us to shunt entropy from the target atom to the auxiliary atom. To do this, what we need is some sort of coupling between these two atoms. A typical coupling is of the form A B dagger plus A dagger B. What is the physical meaning of this term A B dagger plus A dagger B? Note that A is the annihilation operator for this atom and B is the annihilation operator for this atom. Furthermore, remember that the annihilation operator reduces the occupancy of the Fock state by 1, right? And the creation operator, which is A dagger, increases the occupancy of the Fock state by 1. So what is the meaning of this Hamiltonian? The meaning of this Hamiltonian is that we would actually like to reduce the number of excitations in this atom and transfer the excitations to this atom, which will then subsequently be damped away. For hermiticity, we need the Hermitian conjugate of this, which is A dagger B. This explains the sideband cooling interaction Hamiltonian. So how is this implemented for our physical system, which is the ion trap? So let's look at that. In our physical implementation, there are two modes as well. The first of these is the electronic states of the trapped atom. For instance, let's consider calcium. A good qubit is represented below. The vibrational modes of this atom represent the other degrees of freedom. So let's see how both of these modes are used to cool the atom. Consider the electronic state 0 and the phononic state 2. What this means is that the electronic state is in the ground state, and the phonons, which are quantizations of the vibrational modes. So let's see how sideband cooling is implemented with these two modes. Consider the following transitions. So consider the state 0, 2, where 0 refers to the electronic degree of freedom and 2 refers to the vibrational degree of freedom. What we want to do is cool this vibrational degree of freedom. So what we would like to do is transfer this excitation to the electronic degree of freedom. So there is something called the sideband transition, the red sideband transition in this case, which I will describe in the notes for you, which does exactly this. It's the A dagger B plus B dagger A transition. And what it does is it takes 0, 2 and it outputs 1, 1. Here, this 1 refers to the electronic degree of freedom, having an occupancy of 1. And the other 1 refers to the fact that the phononic degree of freedom still has an occupancy of 1, which is to say 1 phonon. This is damped quickly, and we find ourselves in the state 0, 1. Again, a repeated application of the red sideband transition takes us to the state 1, 0. So this excitation is transferred from here to here, and it takes us to the state 1, and it leaves the phononic degree of freedom in the state 0. And this again decays quickly to 0, 0. And because this is now the ground state, there is no occupancy for this transition to go anywhere, and the cooling has been completed. So this procedure of combining Doppler cooling with sideband cooling allows us to get extremely cold atoms, which are then useful to do quantum computing. So let me briefly discuss how gates are implemented in an ion trap quantum computer. The route to implementing quantum gates is represented in this slide. We have a quadrupole Hamiltonian which is proportional to the sigma x, and this allows us to make transitions between 0 and 1. Furthermore, to perform multi-qubit operations, the following interaction Hamiltonian is available, which is of the form A sigma plus e to the I5 plus A dagger sigma minus e to the minus I5. Note that this is exactly of the same form as before. It has the form A B dagger plus A dagger B, but instead of the second harmonic oscillator mode, we have a single spin. This, I will show in the notes, allows us to perform both single qubit gates and 2 qubit gates. Let me summarize briefly. In this lecture, we saw that nuclear magnetic resonance qubits are not good qubits. We considered an alternative, which was trapped ions. We considered the issue of trapping ions, and we saw that Earnshaw's theorem implies that electrostatic potentials cannot trap ions. We then considered this spinning saddle example and motivated the Paul trap. we saw the vibrational modes of the Paul trap and considered motion along the axis and in the transverse direction. We discussed heating and we discussed how to resolve heating. In cooling, we discussed two separate things. One was Doppler cooling very briefly, and the other was sideband cooling. Finally, we discussed how gates could be implemented in the ion trap quantum computer. Thank you very much.